Let's say I have some random variable x, and it is a continuous. It is a continuous random variable, and I want to explore its probability distribution. In fact, I want to construct a probability distribution for it. So let's draw here on the vertical, or on the horizontal axis, I should say. These are the values that x can take on. And in the vertical axis, I'll essentially say the probability density for each of those values. And we'll discover in a few moments why we are calling it density. So let's say that my random variable x, it can never take on negative values. So it's a 0 probability density of taking on any value that is negative. And then it has a uniform density of taking on any value between 0 and 5. So let's say that that's 0. Let's say this is 1, 2, 3, 4, 5. And then it can't take on any value above 5. So it's not going to, it has a 0 probability of any value greater than 5, 0 probability of any value less than 0, and uniform probability between 0 and 5. So this is a shaded in circle, uniform probability between 0, 0, and 5. So this right over here, when we're talking about a continuous probability distribution, this can also be referred to as a probability density function. Probability density function, sometimes a PDF. Probability density function. In this case, you might notice it is a uniform. It is a uniform probability density function. Now, the first question I have for you is, what is the height, or what is this level? We see it's uniform, but uniform at what level? What is this value going to be where this horizontal line intersects the vertical axis for our probability density function? Well, to think about it, we just have to realize that whether we're talking about a continuous random variable or a discrete random variable, the sum of the probability that you get any one of the possible outcomes, the sum of all of those have to be equal to 1. You have a 100% chance of getting one of the possible outcomes for your random variable, whether it's discrete or continuous. So the sum, in the case of a discrete, we kind of summed up the bars. In a continuous random variable, we have to realize it can take on any value, not just 1 or 2 or 3. It could take on 3.14159, keeps going on and on and on forever. It could take on the value of pi. It could take on the value of 2.71, on and on and on, the number e. It could take on square root of 2, and any number in between. So when we're thinking about all of the possible scenarios, all of the possible values that our random variable can take on, times the density, the probability actually is now the area. The combined probability of all of the possibilities is now this area. So for this random variable, in order for this to be a legitimate probability density function or probability distribution, the area here that I've highlighted in orange, this area here needs to be equal to 1. So if this area needs to be equal to 1, and given that this base here is of length 5, what does this height need to be? Well, 5 times what is going to be equal to 1? 5 times its reciprocal. So we have a uniform density right here at 1/5. So given that we've defined this probability density function in this way, let's think about some probabilities. So what if I were to ask you the probability that x is greater than 1, let's say greater than or equal to 1, and less than or equal to 2. What is this probability going to be equal to? Well, you just have to say, well, what are all the possible values that x can take on? So it can be between 1 and 2, including 1 and 2. And so here is its combined probability that x is in that range. It's going to be the area under the curve in that range. And so what is this area? Well, the base here is 1. The height here is 1/5. We haven't drawn the height to scale here. Base here is 1. Height is 1/5. So it's going to be 1 times 1/5, which is equal to 1/5. Let's think about another one. What is the probability that our random variable is greater than or equal to 4 and less than or equal to 4 1/3? What's that probability going to be equal to? So once again, what's the range? We can be greater than or equal to 4. greater than or equal to 4, and less than or equal to 4 1/3, which is right about there. So what we really care about is the area under the curve in this range. And lucky for us, this is a rectangle. So the base between 4 and 1/3, you have a distance of 1/3. And then the height, once again, is 1/5. Times 1/5 is equal to 1 over 15. Now let's do something interesting. What is the probability? Not that the other stuff wasn't that interesting, but let's do something even more interesting. What is the probability? That x is greater than or equal to 3.9 and less than or equal to, actually let me do it this way, 2.9. Let's say x is greater than or equal to 2.9, or 2.9 is less than or equal to our random variable, which is less than or equal to 3.1. That didn't look like an x. And it's less than or equal to 3.1. What is this probability going to be equal to? So we have this little range here, right over here. The height is 1/5. We've seen that over and over again. But what's the area of this rectangle? Well, the base here is between 2.9 and 3.1, so that is 0.02. Let me draw that rectangle a little wider. So if we draw it like this, zoom in a little bit. This point right over here is 2.9. This point right over here is 3.1. The difference between the two is 0.2, or you could say it's 1/5, so 0.2, and then the height here is 1/5. So the base is 0.2, or 1/5, and then the height is 1/5. So it's 1/5 times 1/5 is equal to 1 over 25. Well, you say, well, how is that any more interesting than what we just did? Well, let's escalate a little bit. What's the probability, not of that range? Let's take the probability that 2.99 is less than our random variable, which is less than or equal to. 2.99 is less than or equal to our random variable, which is less than or equal to 3.001. What is this going to be equal to? So now we've made our range a little bit smaller. Our base now is going to be 0.02. The difference between 3.01 and 2.99 is 0.02. So it's now 0.02 base and the same height, 1/5. So the base is now not 1/5, but 1/50th. That's the same thing as 0.02. And we multiply that times 1/5 gives us 1, let me scroll over to the right a little bit, 1 over 250. And we could keep going. And I think you see why this is getting interesting. What's the probability that 2.999 is less than or equal to our random variable, which is less than or equal to 3.001? What's this going to be equal to? Well, same exact logic. The range, the base, this little range of our random variable, it is now a range of 1/500th, 0.002, 1/500. So it's now going to be 1 over 500 times the height, times 1/5, which now gives us 1/2500th. 1/2500. So you see we're getting closer and closer to x being exactly 3, and our probability is getting lower and lower and lower as we narrow our range, as we start getting really, really, really close to 3. So with that, let's just finish this video with a very philosophically interesting question. What is the probability that my continuous random variable defined this way, what is the probability that it is exactly equal to 3? Not 3.01, not 2.9999999. What is the probability that it is exactly equal to 3? Well, now our rectangle has essentially degenerated, or I guess it's degraded down to just a vertical line. Its height is still 1/5, but it has absolutely no width. It is an infinitely skinny rectangle. And so your probability here, it has no area. So the probability is 0. So you actually have a 0 probability of getting exactly 3. Not 2.999, not between 2.9999999 and 3.0001. We're talking about infinite precision. Getting exactly 3, the probability is 0. And hopefully this little progression that we saw gives you an indication of why that is. As we get to a tighter and tighter range around 3, the probability was getting closer and closer to 0.